Okay, so we are ready to work on our last few rules for derivatives. And one I want to start with that we're kind of familiar with is the, derivatives of the general exponential functions. I want to look at those. We know the derivative of the natural exponential function. When we say natural, what are we talking about? Natural exponential function means the base is e, the natural base, right? E being a number about 2.718. And we know the derivative of this function is itself, basically, right? Or at least that's what we had observed way back at the beginning of our rules for derivatives. Okay? But now we're going to derive the general exponential function. So the base here in general exponential functions can be any real number that is positive and not equal to 1. So here's our general exponential function. So I can have e to the x. I can also have like 2 to the x, 1/2 to the x, 4 to the x, etc., etc. As long as the base is positive and not equal to 1. If you remember those graphs, if the base a is greater than 1, like for instance like e is greater than 1, then the graph of the function is increasing on its domain. Of course, the y-intercept is at 0, 1. This would be true for any exponential function because a to the 0 power is always equal to 1, right? If the value of a is between 0 and 1, then the function is decreasing on its domain. And we still have that same y-intercept, right? Both functions' domains are all real numbers, regardless of what the base is. The domain is all real numbers. The range is everything greater than 0. And we have horizontal asymptotes of y equals 0 in both cases. The case where a is greater than 1, we approach the horizontal asymptote as x goes to negative infinity, and for values with a base between 0 and 1, like 1/2, we approach the horizontal asymptote as x goes to positive infinity. Okay? So we're going to find the derivative rule for these type functions. Okay? And then we'll see that it also works for the one case where we know with the base is e. And I'm going to do this using the inverse property between the exponential and logarithmic functions. So recall from that e to the natural log of a is equal to a. Okay, so the logarithm, right, the natural log here, right, this is ln, it stands for logarithmic natural. This is log base e, okay? And so remember what a logarithm is. It is an exponent, right? And that's exactly what a logarithm is an exponent. So the natural log of a is basically the power or exponent on the base, which in this case is e, that you need to get a. In other words, if I raise e to this power, I'm going to get a. That's what the natural log is. And you can see they're inverse operations, right? If I take a and plug it into the natural log function, I get some output, right? Natural log of a, whatever that is. I plug that into the e to the x function, right? I get back to a. Right? They cancel each other out. And this is true for all values of a greater than 0. Okay? And we're going to use the chain rule to find the derivative. So let's proceed then. We start with the derivative of a to the x. And what I'm going to do is I'm going to rewrite a in a crazy manner. Right, here's a. I'm going to write a as e to the natural log of a. You might wonder why in the world would we want to do that. A is e to the natural log of a. So this is a all to the x power. All right, so e to the natural log of a is equal to a. So I've just replaced a with that expression. And now what do I have? I have e to the natural log of a. That's some real number. So e to that power. And then I'm raising that to another power. What do we do when we have an exponent, right? An exponential expression, and then we raise it to another. What do we do with these exponents? Do you remember what we do? We multiply. And so this is the same thing as e to the natural log of a times x. Natural log of a times x. Okay. Now remember, the natural log of a is a fixed value. A is any real number greater than 0, not equal to 1. Right? So a could be 1/2, a could be 2, a could be 3, or whatever. And so if a is 2, then natural log of 2, that's a real number. Natural log of a is a real number. So this is e to the power what? Some real number times x, of just a real number multiple of x is our exponent. And so this is finding now this derivative. Lo and behold, this is a chain rule. Remember, we know the outer function here is e to the u, and I know the derivative, right, of e to the x, right? It's just e to the x. And here the outer function is e to the u. And the inner function is what? Natural log of a times x. So it's by chain rule, right? We have that this is equal to the derivative, e to the u, the derivative of the outer function. And what is u? It's the natural log of a times x, times the derivative with respect to x of that inner function. And that's the chain rule. So the derivative of the outer, derivative of the outer function, right? E to the u, derivative of e to the u is e to the u, where u is natural log of a times x. Chain rule says times the derivative of the inner function times the derivative with respect to x of u. So the question is, what is this? Okay, what is this? So remember, natural log of a is a constant. It's a real number, right? A is some fixed number. So this is a constant multiple. I can pull that natural log of a out. What's the derivative with respect to x of x? That's just 1. So this is just natural log of a. Right? I mean, if I had the derivative with respect to x of 3x, you'd say the derivative is 3. So this is the same thing. Constant multiple of x. Right? This is just a linear function with slope natural log of a. Okay? And so we really have our answer now. I'm going to rewrite e to the natural log of ax, because remember, that was what we had started with. That's in the parentheses here, which is equal to this, which is just a to the x. This indeed is a to the x. And so what we have here is the rule now that the derivative with respect to x of a to the x is the natural log of a times a to the x. So it's natural log of a is just a real number. So the derivative of any general exponential function is the function itself times a constant, right? A constant multiple of the function. So this is the general exponential function rule. And notice it does indeed work if I take the derivative with respect to x of, say, e to the x, and I use this rule. It says natural log of the base is e this time, a is e, times e to the x. But what's the natural log of e? What's the power of e needed to get e? E to what power equals e? Answer 1, right? Natural log of e is 1. And this is just e to the x. And so it works for what we know. However, if I take the derivative with respect to x now of, say, 2 to the x, right, by this rule, it's the natural log of 2 times 2 to the x. Okay. So it's a scalar multiple. And natural log of 2, you can use your calculator to approximate if you want to, get an idea of what that is. But again, that's just some real number. It's a real number multiple of the original function is the derivative. Okay. So let's now apply this with all the rules that we have before. Let's throw it in with the product rule, quotient rule, chain rule, rules for the trig functions, etc., right? Power rule, constant multiple rule, all those rules. Let's throw it in with those. So we have this rule we'll put up at the top here that we just developed. And let's find the indicated derivative here. Dy dx if y is equal to x squared times 2 to the x. So what rule do I have to use to find this derivative? I've got a 2 to the x, so obviously I know, we just did that down here. I've got to know how to do that, right, from this general exponential rule. But I've got x squared times 2 to the x, so I've got a product rule. All right, product rule. And so dy dx is take the derivative with respect to x of x squared times 2 to the x plus x squared times the derivative with respect to x of 2 to the x. That's the product rule. The derivative with respect to x of x squared, that's just power rule, right? That's 2x, that's easy. Notice the difference between this one and this. Right here, the base is variable, the exponent is constant. That's power rule. But if the base is constant and the exponent is variable, that's the general exponential function rule we just developed. As we saw, this will be the natural log of the base, which is 2 times 2 to the x. And so I get 2x times 2 to the x. And I want to sort of emphasize that I want to make sure that 2 to the x, this 2x doesn't, this exponent is only working on the 2, not the 2x. So be careful about that. Plus what? Natural log of 2 times x squared times 2 to the x. Let's bring this natural log of 2 in front. It's just like a real number. It's like 3 or 4. Natural log of 2 you can punch in. It's a real number, times x squared times 2 to the x. And there's our answer. Again, you can factor some stuff out of here. If you want to factor out an x and a 2 to the x, you can. But that's sufficient for right now to give us the result. Okay. Let's look at the second one. What rule do we have to use here? Find g prime of t if g of t is sine of 5 to the t. This is a composition of functions, so we have to use what? Chain rule. This is a chain rule. Right? So the outer function is sine, inner function is 5 to the t. This is not a product. This is not sine times 5 to the t. It's sine of 5 to the t. So chain rule says that g prime of t, derivative of the outer function, what's the derivative of sine? It's cosine. Evaluate at the inner function times what? The derivative of the inner function. And what's the derivative with respect to t of 5 to the t? That's by this new rule, remember? Right here. Of course, I've got x here, but down here our independent variable is t. But the derivative of a to the t would be natural log of a times a to the t. And so here we have the natural log of 5 times 5 to the t. So I'll clean that up. I could bring the natural log of 5 in front. I'll bring this 5 to the t in front as well. Cosine of 5 to the t. There's our derivative. Look at one more here. Find the dz dr if z is equal to 4 secant r. Secant r. Okay. So what do we have here? We have a composition again. We have the outer function is 4 to the u, 4 to some power. The inner function is secant r. So we've got a chain rule going on here. This is a composition. And the outer function is 4 to the u, right? How do I take the derivative of the outer function? What is the derivative of 4 to the u? Well, that's our new rule. It's the natural log of the base, 4, times 4 to the u, where u is secant r. Looks like secant r. Okay. So again, this was chain rule with the inner function was u equal secant r. And the outer was z equal 4 to the u. Right, so we took the derivative of the outer function here. 4 to the u is natural log of 4 times 4 to the u. That's the new rule we just learned, where of course u is secant r, times the derivative with respect to r of that inner function. Right. And what is the derivative with respect to r of secant r? You remember the derivative of secant is secant r tangent r. Okay. And so our final result is natural log of 4 to the secant r. This time I'll just not write with any parentheses around those the r's. Secant r tangent r. So again, you're looking at some crazy looking derivatives here, but this is the process of learning how to apply these rules. All right, let's finish this particular video with this example here. The find y prime if y is equal to 3x plus 1 to the pi power plus pi to the 3x plus 1 power. Seems like we did a little dosage, swap there. And then plus pi to the pi. Okay. So let's see what we have here. I've got the sum of three functions, so I'm going to take the derivative of each one by the sum rule. And what do I got here? I got chain rule, right? What's the inner function here? Inner function here is 3x plus 1. So here on this one we got a chain rule, right? The inner function is u equals 3x plus 1. And the outer is y equal u to the pi, right? So it's chain rule. Chain rule. Observe the outer function u to the pi is what? Bring the pi down. This is power rule, right? Since the base is variable and the exponent is fixed. 3x plus 1 to what? We subtract 1 from pi, pi minus 1, times the derivative with respect to x of 3x plus 1, the inner function. Of course, the derivative with respect to x is of 3x plus 1 is just 3. So again, this right here, that was the chain rule. Okay. Plus the derivative here. Well, guess what? This is chain rule again, but now the inner function is still 3x plus 1, but the outer function is the inner. But now, what's the outer? Outer is y is what? Pi to the u, right? So now, is this a power rule? Do I bring the u down and subtract 1? No. U is the variable part. Pi is now fixed. This is general exponential, like a to the x. This is a fixed base to a variable exponent. So that's going to be our new rule. It's the natural log of the base, which is pi, times pi to the u, and what's u? 3x plus 1, times the derivative with respect to x of 3x plus 1. Right. So here's chain rule now for this one. Right. Of course, this derivative is just 3. So I took the derivative of the first one, derivative of the second one is here, plus the derivative of the third one. What's the derivative of the third one? What's the derivative of pi to the pi? Well, be careful here. What rule am I going to use here? Pi to the pi is a constant. Pi to the pi power, there is no x variable at all. Pi raised to the pi power, you can use your calculator to approximate that. If I graph the function y equal pi to the pi, it is a horizontal line. It is a horizontal line. It's a constant. What's the derivative of any constant? 0. Okay. So just kind of get you an idea how we can interchange, right? Here the base is variable, exponent fixed. Right, so we're talking about chain rule with the derivative of the outer function being the power rule. So this is really a generalized power rule. But pi here is the base fixed, right? Constant. The exponent is now variable. That's a general exponential rule for the outer function in that chain rule. Okay. So our final result is 3 times pi. Bring that 3 in front. 3x plus 1 to the pi minus 1. And then here, I've got this 3 pulled in front, plus 3 times the natural log of pi times pi to the 3x plus 1 power. So it is real important to differentiate between when you have a power rule versus the general exponential function rule. And here's the whole thing, right? Power rule is going to be what? If the base is variable and the exponent is fixed. General exponential rule, the base is fixed, a constant, and the exponent is variable. Okay, So we're going to look at the logarithmic functions and their derivatives in our next video.